Today we look at sum and difference formulas, and we're going to use these formulas to find exact values of trig functions. So these are our sum and difference formulas. We have a sum and a difference formula for both sine and cosine. These formulas involve us using two angles. And the two angles are alpha and beta. So we're always going to be working with two reference triangles when we're working with these formulas. Notice you've got a formula written for sine of alpha plus beta, and it goes sine of alpha cosine beta plus cosine of alpha sine of beta. The difference formula for sine looks like this. Sine of alpha minus beta is equal to sine of alpha cosine beta minus cosine alpha sine beta. Okay. Cosine of alpha plus beta is broken down like this. Cosine alpha cosine beta minus sine alpha sine beta, and then cosine of alpha minus beta is equal to cosine of alpha cosine beta plus sine alpha sine beta. That's not a typo, by the way. The sum formula for cosine does involve subtraction, and the difference formula for cosine does involve addition. So basically, what you need to do in these problems is you are going to need to draw two reference triangles. So you'll draw a reference triangle for angle alpha, and you'll draw one for angle beta. Now, these reference triangles might be based on special angles where I don't know, we're going to have to use those 30, 60, 90, and 45, 45, 90 reference triangles. So those reference triangles, and then we're going to have problems that just involve like a regular ratio and not a special angle. But I'm going to start with the special angle ones. So previously, I just reviewed with you all on how we can find exact values at these special angles. And what makes these like easier for us to do is I also shared with you this diagram with the quadrantal angles, the 30, 45, and 60-degree reference angles. And so these are going to be helpful to us here as well. It's going to make, well, drawing those reference triangles for our two angles much easier. In example 1, it says use a sum or a difference identity to find the exact value of the expression. And I want to find the exact value of sine of 2 pi over 3 plus pi over 4. So those are my two angles, alpha and beta. So alpha is 2 pi plus 3, 2 pi over 3, and then beta is pi over 4. So I'm going to want to first draw my two reference triangles, one for alpha and one for beta. And this is going to be easy to do because I have these diagrams here. So for 2 pi over 3, I'm going to have a 60-degree reference triangle. And for pi over 4, I'm going to have a 45-degree reference triangle. And so I already drew those here. Notice I am getting all my info from these diagrams. So for 2 pi over 3, notice that I drew that triangle here, but I also paid attention to the fact that we're in quadrant 2, and in quadrant 2, my x values are negative and my y values are positive. Pi over 4 is in quadrant 1, so I'm basically just copying this diagram as is. And so that's the first step, is to draw the two reference triangles. Now, sine alpha plus beta, because that's what we're looking at here, is sine of alpha plus beta. Its formula is broken down as sine of alpha cosine of beta plus cosine of alpha sine of beta. So what I'm going to do is I'm going to use these two reference triangles, and I'm going to find those 4 exact values. All right, so I'm going to have to use my triangles to figure out what is sine of alpha. And so if I look at triangle alpha, I notice that sine is the opposite over the hypotenuse, the opposite being the square root of 3, the hypotenuse being 2. And then I go on to the next part. And the next part is, what is cosine of beta? So pay attention to alpha or beta. Which triangle are you working with? Because you don't want to work with the wrong triangle, because now I'm working with beta, and that's my second triangle. And cosine is the adjacent over the hypotenuse. So I'm looking at the square root of 2 over 2. So then I'm going to continue on in this manner. So cosine of alpha, alpha is my first triangle. So cosine would be the adjacent over the hypotenuse. And then lastly, I have sine of beta. Beta is my second triangle, and sine is opposite over hypotenuse, so square root of 2 over 2. So now I've found these 4 exact values. I'm ready to do some math. Don't want to lose that plus sign. So when I multiply 2 fractions together, this is actually really easy to do. I simply multiply the numerators together. So the square root of 3 times the square root of 2 is the square root of 6. So when I multiply square roots, I just multiply the insides with the insides. On the bottom, I have 2 times 2, and that's 4. Plus, over here, if I go -1 times the square root of 2, I get negative square root of 2. And then on the bottom, 2 times 2 is 4. So basically, if I write this as one fraction, I have the square root of 6 minus the square root of 2, because I have that plus and negative, all over 4. And that's my final answer. Like, I am going to leave it just like that, because you can't actually subtract like the square root of 6 minus the square root of 2 and get like the square root of 4. It doesn't work that way. So we just leave it like that. Okay. But that's how you use these sum and difference identities. And then these particular ones, we were working with those special angles. So why don't you try the few that are on your Google form, and then we'll take a look at some other types of these problems.